Okay, so I hope everyone is awake and ready to have fun and enjoy. What we're going to start talking about today is open systems. So previously we've been talking about closed systems, right? So closed systems, remember, are systems that don't have mass transfer. And what we'll start talking about today is systems that do have mass transfer, and those are called open systems. And so as an example, what I show here is a schematic of a jet engine. Okay, so here is a jet engine. And this is also schematically very similar to a natural gas power plant. Okay, but in a jet engine, you have several different components. Air flows into the jet engine through a diffuser, which slows it down. Then it goes through a compressor, which raises it to a high pressure. And then it goes through a heat exchanger, which allows combustion to occur and allows heat to exchange between the exhaust gases and the air. And then they go through turbines, which produce a work output. And then eventually they go through a nozzle, and at the end of the jet engine, they create thrust. Okay, so the idea here is that this is an example of an open system. This is actually several different open system components all linked together. In this class, we're going to focus on analyzing each one of those components individually. When we move on to the second semester of thermodynamics, then we'll start looking at how we analyze these systems as a whole. But I just wanted to show this as an example of a thermodynamic system that has mass flowing through it. Okay, so the air is flowing through this engine continuously flowing in the front, continuously flowing through the compressors, through the heat exchanger, through the turbines, and then flowing out the back through the nozzle. Okay, we'll eventually get to the point of talking about how we analyze each of those individual components in turn. But before we talk about each of those components, let's talk about how we analyze open systems in general. So open system analysis is commonly referred to as control volume analysis, but really it's not any different than closed system analysis in that we draw a control surface and we use that control surface to track transfers and changes inside. But there will be a few differences. Okay, so whereas previously we focused on closed systems, and typical closed systems that we saw were things like piston cylinders and rigid tanks being the most common too. Previously, we also dealt with quantities. Okay, so with a closed system, typically you would have a quantity of mass experiencing a quantity of energy transfer. And those things are going to be a little bit different as we move on to open systems. So now as we deal with open systems, mass is going to be able to flow in and out. And instead of dealing with quantities, we're going to deal with rates. Okay, so we're going to have rates at which mass moves or transfers. We're going to have rates at which energy transfers. Okay, so instead of talking about an amount of heat transfer that occurs, we're going to talk about the rate at which heat transfer is going to be continuously occurring. So as an example, let's start off by looking at the mass balance. Okay, so let's imagine, when we were talking about closed systems, we had one person with a given number of marbles throwing them at another person. And we looked at what the change in marbles was as we drew a box around one person, or we drew a box around another person. And that was pretty simple. The change in marbles for somebody was equal to the marbles in minus the marbles out. Really simple mass balance. When we look at open systems, it's going to be pretty simple again, but instead of looking at quantities, we're going to look at rates. Okay, so for example, let's imagine that person A, instead of throwing two marbles, let's imagine that that person is throwing two marbles per second at person B. Let's imagine that person B is throwing one marble per second back at person A, but that maybe they're also throwing four marbles per second at person C over here. And person C, maybe they're throwing 2 marbles per second at person A as well. So now we can do a mass balance on each of these individuals that looks at rates instead of quantities. So let's imagine that we focus on person B and we do a mass balance for person B. You should be able to tell pretty obviously that if 2 marbles per second are coming in and 1 marble per second is going out and another 4 marbles per second are going out, that means that 5 marbles per second are going out. So 2 per second coming in, 5 per second going out means that every second person B is going to lose 3 marbles. Okay. To put that a little bit more mathematically, the rate of change of marbles for person B, we're going to call that m dot CV for control volume. It's the rate of change of marbles or mass inside the control volume, is equal to the sum of the rate at which marbles are coming in minus the sum of the rate at which marbles are going out. So we're going to sum this over everywhere it's going in. We're going to sum it uh, everywhere it's going out as well. And this should be fairly obvious. If you and think of rates instead of quantities, they still add the same way. If you make $10 an hour and spend $2 an hour, you make $8 an hour, right? And that's just kind of how things add up. Whether you're looking at rates or quantities, they still add in the same ways. So to make that a little bit more explicit, let's imagine an analogy with money, because remember, this whole class is about energy accounting, and accounting is the same whether you're looking at dollars or energy, right? So let's imagine that you earn $50 a day doing work, but let's imagine that you spend $20 a day on food and maybe $5 a day on utilities. You should pretty quickly be able to recognize that that means that you are gaining, or another word for that would be accumulating, $25 per day. Okay? Whether you're adding up money or whether you're adding up energy, whether you're adding up mass, they all add in the same ways. Rates add the same way that quantities add. But now we need to introduce a new term, and it may be a term that you've seen in some of your other classes, but if not, we're going to go through it again here. Okay, so that term is steady state. And what steady state is defined as is it means that there's no change with time. Okay? It doesn't mean that nothing's happening. It just means that whatever it is that's happening is the same now as it is 5 minutes from now. There's no change with time. Okay? And so let's look at what this means. Well, in particular, the most important thing that steady state means is that there can't be any accumulation, right? Because if we go back to this little earning and spending analogy, right? If you are earning more than you're spending, then that means that your bank account today is going to be different than your bank account tomorrow, right? So it's not the same with time. It is changing with time. That means it's not in steady state. Alternatively, let's say that you're spending more than you're earning. That means that your bank account is depleting. If your bank account is depleting, then that means that tomorrow it's going to have less money in it than it does today, which means that it is changing with time. If it's changing with time, it's not in steady state. So when we say that something is in steady state, what we are saying is that there is no change with time. And if there's no change with time, there's no accumulation. If there's no accumulation, what that means is that the rate of change or accumulation of mass inside a box has to be equal to 0. Because if there's no change with time, then nothing is allowed to accumulate or deplete. And later we'll talk about the similar case with energy, where steady state means that energy is not allowed to accumulate inside a box either, which means that energy flows in have to equal energy flows out. Just like here, what this means is that mass flows in have to be the same as the mass flows out. To go back to the marbles, what that means is that the rate at which marbles are coming in has to equal the rate at which marbles are going out. Otherwise, you're going to accumulate marbles. Now, what if we're not in steady state? And by the way, we're almost always in steady state in thermodynamics. Most systems that have stuff flowing through them are flowing through continuously. But in the event that you were not in steady state and you wanted to know what's the change in mass over time or what's the accumulation over time, what you would need to do is you would need to integrate the accumulation over time. So if you wanted to know change in mass, that would be equal to the integration of the rate at which mass accumulates over time. So from time 0 to some time t. And that's analogous to when in physics 1 you would calculate a displacement and it was equal to the integral of the velocity over time. Velocity is a rate of change of distance, so you integrate that rate of change over time and it gives you a displacement. Same idea here. You integrate the accumulation over time and it gives you a change in mass. I don't want to spend too much time on this. We're not going to emphasize it in this class, but I do just want to quickly mention that that is how you would calculate a change over time if you were not in steady state. But most of what we're going to focus on in this class is going to be steady state. Okay, now hopefully most of that stuff was fairly clear. And what I need to do now is I need to add an additional concept that's going to be important later. And that concept is how we evaluate mass flow rates. And that's important because it's actually hard to measure a mass flow rate directly, but what is easy to measure is velocity. So what we want to be able to do is we want to be able to evaluate a mass flow rate from a velocity and be able to go back and forth between the two. So to help us think through this, imagine that there's a pipe, okay, just a simple pipe with some fluid flowing through it, okay, and that fluid is flowing through it with some velocity v. Okay, I usually write my velocity v's with a little line over the top, just so that you can tell the difference between a velocity v and a specific volume v. Okay. Now, as you'll learn in fluid mechanics, it turns out that there's actually a velocity profile through the pipe, and it's not actually uniform across the cross-section. We're not going to deal with that in this class. This is thermodynamics. It's a little bit simpler. We're just going to focus on the idea that there is some average velocity that the fluid is moving through the pipe. And the question is, how do we determine the mass flow rate from this velocity? Okay. To help us think through this, let's play a little mental game really quick. Let's imagine that we draw a little hypothetical line somewhere in the pipe through the fluid. Okay. And let's imagine that we're going to track this little line of fluid as it moves through the pipe. Okay, so sometime later, this little line of fluid has moved forward through the pipe, and it's now at this location. It should be fairly obvious for you to recognize that the displacement that that fluid moved is going to be the velocity times the time interval, right? Because velocity times time gives you displacement. So that's how far the fluid moves in some time period delta t. Okay. Now, what should also hopefully be clear is that the volume of fluid that moved past that line is equal to that volume right there. Okay, so this is the volume of fluid that moved in delta t. Okay, and using basic geometry, we can determine what that volume is. That volume is going to be the area of the pipe times the height of the pipe, which is velocity delta t. So that means that the volumetric flow rate is equal to the volume that moved divided by the time interval, right? So that's the rate at which volume is flowing, how much volume per time. The time interval was delta t. The volume is area of velocity times delta t, which we then divide by delta t. The delta t's cancel. And so the volumetric flow rate by definition is the area of the pipe times the velocity of the fluid. And this, by the way, is the symbol that we're going to use for volumetric flow rate. For those of you that have taken fluid mechanics or will be taking fluid mechanics, you might notice that this is different than what's commonly used in fluid mechanics. The reason is that in fluid mechanics, you commonly use Q as a volumetric flow rate, but we use Q as heat transfer in thermodynamics. So in order to avoid confusion, we use area times velocity to signal volumetric flow rate. But volumetric flow rate isn't really what we want. What we want is mass flow rate. And the symbol for mass flow rate is m dot. And you should recognize it should be fairly straightforward that if you take volumetric flow rate and you multiply it by the density, that should give you mass flow rate, because density is mass per volume. So if you take mass per volume, multiply it by volume, that gives you mass, right? But we don't use density in thermodynamics. Instead, we use specific volume. So volumetric flow rate divided by specific volume is equal to volumetric flow rate times density, because remember, density by definition is 1 over the specific volume. And this is the key equation that I was hoping to derive here, which is that the mass flow rate at a given location is equal to the area of the pipe times the velocity, which gives you the volumetric flow rate, divided by the specific volume. Okay, so that is what I was looking for. Okay, mass flow rate is equal to volumetric flow rate divided by specific volume. And quickly, let's just make sure these units work out. That gives us m dot is equal to area, which is a meter squared, times velocity, which is a meter per second, divided by specific volume, which is meters cubed per kilogram. Meter squared times meter is meter cubed. That cancels with meter cubed. Kilogram is on the bottom of the denominator, which means we can pull it up to the top. And so that means we get kilograms per second as our units for mass flow rate, which sounds about right. Okay, so let's do an example. This is problem 422 out of the book. As we work through it, let's read it. All right, so ammonia enters a control volume. So step 1 is identify our substance, which in this case is ammonia. So it enters a control volume operating at steady state. Okay, so we can't draw a diagram yet. We don't know what we're looking at, so we'll skip that for now. But we'll start writing down property and process information. So it enters a control volume operating at steady state. That's important. Let's write that down. At a pressure 1 of 16 bar and a temperature 1 of 32 degrees C with a mass flow rate. So mass flow rate at the entrance, which is m dot 1, because that's where we're tracking everything. M dot 1 is 1.5 kilograms per second. And it says that saturated vapor at 5 bar leaves through one exit and saturated liquid at 5 bar leaves through a second exit. Okay, so now we can draw our diagram. Okay, so we have a control volume which has one inlet and it has two exits. Okay, so we'll call it the inlet state 1, exit 2 and 3. Okay, and we know that at one of the exits, we have saturated vapor. So we'll call that exit 2 where saturated vapor is there. So X2 is equal to 1, which is the quality of a saturated vapor. And P2 is 5 bar. Okay, so saturated vapor at 5 bar leaves through one exit, and saturated liquid at 5 bar leaves through the other exit. So X3 equals 0, and P3 also equals 5 bar. Okay, so looking at this, one thing that you should notice is that you have two properties at state 1, two properties at state 2, and two properties at state 3, which means we can get all other properties as necessary. Okay. We also know that the saturated liquid at 5 bar leaves through its exit with a volumetric flow rate of 0.1 meters cubed per minute. So that means that the volumetric flow rate at 3 is equal to 0.10 meters cubed per minute. It's important to make sure that we put that 3 in there because we need to recognize that that's the volumetric flow rate at that exit, which doesn't mean that that's the volumetric flow rate anywhere else. So the first thing that we're asked to do is we're asked to find the minimum diameter of the inlet pipe so that the ammonia velocity stays below 18 meters per second. Okay, so that means we need some way to relate diameter, which relates to the geometry of the pipe, and velocity to something that we know, which in this case is mass flow rate. Okay, luckily we have a way of connecting mass flow rate to area and velocity. So for part A, this is pretty simple. We just say that m dot 1, we know that that has to equal area times velocity 1 divided by specific volume at 1, right? Because we just went through that, how we relate mass flow rate to volumetric flow rate. We know m dot 1, we have two properties, so that means we can get v1. We know that we need a velocity of 18 meters per second, so we know velocity 1. So we just solve for the area and solve for the diameter because area is equal to pi d squared over 4. So remember that area is pi d squared over 4. And you solve for the diameter, and you should find that the diameter is 1.34 centimeters. Okay, easy enough. That was part A. Part B asks for the volumetric flow rate of the exiting saturated vapor. So that's volumetric flow rate of the exiting saturated vapor, which is exiting at 2. Okay, in order to do this, let's use the tool that we just learned, which is the mass balance for an open system. And the mass balance for an open system says m dot CV is equal to the sum over the inlets of the mass flow rate at each inlet minus the sum over the exits of the mass flow rate at each exit. We know that we're in steady state. If you remember, steady state means no change with time. No change with time means no accumulation is allowed. And if no accumulation is allowed, then that means that m dot CV has to be 0 because that was the accumulation term. That was the difference between what went in and what went out. So if you had more going in than going out, then you'd be accumulating. Accumulating is not allowed in steady state, so that's got to be equal to 0. So 0 equals the sum over the inlets. How many inlets do we have? Well, we only have 1. So there's only one term in that summation, and it's m dot 1 because that inlet 1 is the only inlet. Minus the sum over the exits of the mass that's leaving. We have 2 exits, so that means we need to add the mass flow rate at each of those 2 exits. Okay, we know m dot 1, but that's all we know so far. Well, we're looking for volumetric flow rate at 2, so let's convert m dot 2 into a volumetric flow rate. So that's 0 equals m dot 1 minus m dot 2 is equal to volumetric flow rate at 2 divided by specific volume at 2 plus m dot 3 is the volumetric flow rate at 3 divided by the specific volume at 3. Now let's look at what we have. We know mass flow rate 1. We have 2 properties at state 2. We have 2 properties at state 3. We know the volumetric flow rate at 3. And so all we need to do is solve for the volumetric flow rate at 2. When we do that, volumetric flow rate at state 2, you can find is equal to 5.771 meters cubed per minute. And I'm going to trust you to be able to verify that math on your own. One comment that I want to make here that's really important is that the volumetric flow rate at each of those 3 inlets and exits doesn't have to be the same. You can have different volumetric flow rates at each exit. So that's why we have to put in that little index to make sure we're talking about volumetric flow rate at 2, volumetric flow rate at 3. And if we want to convert from mass flow rate to volumetric flow rate, we need to use the specific volume at that spot as well, because the specific volume can be different in each inlet and each exit because it's coming in and coming out with different properties. Okay, so making sure that we're consistent with those notations so that the volumetric flow rate is matched to the specific volume and the volumetric flow rate is matched to the mass flow rate. Okay, so that's the example, and that is where we will leave it off, and we'll pick this up next time with energy balances for open systems.